Hello, we're going to be doing today substitution problems at alkyl halides and other substrates. So I'm going to give you, this is our first problem today. So we have the following molecule, and then, right, and we have the substituents, and we have a condition here. So your reagent. And that's what you have. And so to solve problems in substitution, we're going to be looking at what is the reagent and what is the substrate, primarily. And also we need to do considerations about stereochemistry when that happens. But first, what we want to see here is that we have this nucleophile, and that molecule does a weak base, but a good nucleophile. Also, we see this here, acetone, that is polar A product. So let's write that down, polar A product. And here, this is a good nucleophile, but is poor base. So now we got to the substrate. The alkyl halide here, and remember when we don't draw hydrogens attached to carbon, so that's a methyl group, CH2, and so forth. Now, where the bromine is a secondary carbon, so that's a secondary alkyl halide. And having those conditions, the reaction that's gonna take place is an SN2 reaction, right? So at the SN2 reactions, remember that if we have a configuration, you're going to have the inversion in the product. Because remember that the attack happens at the back. So just to remember as the mechanism, if we have this, say this is R1, R2, and that's any halide. If we have an SN2 reaction, say that we have a good nucleophile, and it's going to attack here at your alpha carbon, then the attack is from the backside. And so the result, the product has inversion of configuration if this is a chiral center. So now, do we have a chiral center in this molecule? This is the COM if these groups are different and you have a chiral center. But notice that here in this molecule, you don't have a chiral center, even though we have a bromine here, but these two substituents are the same. So because of that, the problem is, say, easier. So, but we're gonna draw anyhow, regardless of that, the substitution, then the SN2. What is going to happen is then the attack over to that carbon, and you're breaking that bond. I'm going to draw it nonetheless with the configuration as is, but remember really if you don't need to specify much a configuration in this particular one. So that will be your product. Again, what did we do? We analyzed first the reagent, so a good nucleophile poor base, a polar A product solvent, and a secondary alkyl halide. So the path here is SN2. So I'm going to do another problem. So let's say erase this one and do one more thing. And that's the type of analysis that you need to be doing when you're doing problems in SN1 and SN2. So now let's go over something else and say that I have now the following substrate. Let me grab another thing. Then my molecule is now, okay, this, I'm gonna have another bromide. And here I have an ethyl group. Condition says here, methanol. And now we need to analyze what is the reagent here. So methanol, it's not a good base, right? But it's still a nucleophile. So in that, alkyl halide here is secondary. So secondary alkyl halide, this here methanol is acting both as is a nucleophile and is a solvent. So in its polar product. So when we have something that's polar product, weak nucleophile. So remember, secondary alkyl halide, depending on the conditions, they can go SN1 or SN2. But these conditions are good for SN1 reaction. And remember, SN1 reactions happen through in stepwise with the formation of a carbocation intermediate. So what you have here then is at first the formation of a carbocation. Again, what was the analysis here? What we have, consider first the conditions. So my reagent is nucleophilic, but it's not a base, a good base. It's also the solvent, and the solvent is polar product, and now my alkyl halide is secondary. Now I have the carbocation intermediate that we see here. But it turns out that at this carbon, we also have a hydrogen. And we know that this carbocation particularly is not that stable. But you can have a 1,2 hydride shift. I'm just going to draw the two lines. So that means that you're shifting a hydrogen with the electrons and migrating that over there. In doing so, you're making a better carbocation. Now this time, after you migrate the hydride over there, you're going to have a carbocation here, and that carbocation is tertiary. So that's the first step. In second, what we have is then the nucleophilic attack. Remember, it's stepwise, SN1, first the formation of the carbocation intermediate. Second step is the nucleophilic attack. And what is the nucleophile? Methanol. So here you will have, they say the nucleophilic attack over here. Also, in this case, you're not going to make a chiral center, but do remember that carbocations are trigonal planar, and if you're making a carbocation, since the attack can be from either side of the plane, you form a racemic mix. Not in this case because you're not making a chiral center. So your initial product is going to be, say, I'm not going to draw any specific configuration, but here you have, it's still protonated, and looks like small in the screen. I see that. Okay, H. And you need another, say, molecule of methanol, this time acting as base, to remove that extra proton. So your final product is an ether. You will have that. Again, I'm not specifying configuration here. I don't have a chiral center in this molecule, right? So again, recap, what did we do? Analyze the reagent. So weak base, but it's nucleophilic, polar A product. So conditions for SN1. And we did the formation of a carbocation in the first step. Carbocation is secondary, so we propose a hydride shift, which will give me a more stable carbocation. And at that carbocation, you will have the nucleophilic attack. We will do more problems on that.